All right, now we're gonna start with a conjecture by a physicist, Dyson, in 1962, which claims the following, and this has been proved. So this was initially Dyson's conjecture in 1962 and proved also by physicists, and proved by Wilson in 1962, Gunson also in 1962 independently. Right, so the conjecture is the following. The constant term in the expansion of the product of 1 minus xi over xj to ai is equal to the multinomial coefficient Now, what does that mean? Well, in other words, if A is equal to sum of ai, then when you look at this, you have this xj to the minus ai term, right? So what you end up is, well, it's a product of, in the product of xj minus xi to the ai, and then you also have aj, right? Because we apply this product for all ij, so let me say this way. And then when you apply aj, we are multiplying minus 1, so minus 1 to the aj. In this product, the coefficient of the product of x to the xi to the a minus ai is equal to a1, a2, an factorial divided by n factorial, a2 factorial, an factorial. Okay? So that's the Dyson's conjecture. And I'm going to show you a proof by Good in 1970. So how do we prove that? So this is by induction on something, let's say sum of ai. So as whenever I reduce n or whenever I decrease the sum of them, then I win by induction. All right. Now, if aj is 0 for some j, then what's going to happen? If something is aj is 0, if this is 0, if aj is 0, then xj, okay, let's say ai to be less confusing. So if ai is 0, then xi will never appear on top, right? It's going to be only appear in the negative exponent, so we will never contribute to anything to the constant term. So in this case, we can ignore all terms of having all the product having a all the product having xi, right? So the coefficient, the constant term of the product of 1 minus xi xj ai. Oh yeah, I need a notation. Let's say I need a notation. So let me move over here. So let f x a1 a2 an be the coefficient, the constant term. Product I not equal to j, 1 minus xi over xj. Okay, so if ai is non 0, then we know that xa1 a2 an is gonna be, we can just ignore aj, so xj minus 1, xj plus 1 up to xn semicolon a1 a2 aj minus 1 aj plus 1 an, and by induction this is equal to a1 plus. Okay, why is this true? Because by induction what we know is that it's equal to aj minus 1 and aj plus 1 up to am factorial divided by a1 factorial up to aj minus 1 factorial, aj plus 1 factorial up to am factorial, right? But that's equal to this. Now, so therefore I can assume that none of AIs are 0. Oh, by the way, I can also assume, we may assume n is bigger than 0, right? So what's left? Well, n is bigger than 1, let's say. So we may assume i's are non-zero for all I. Now here's an interesting fact. So let fjx the product of x minus x I divided by the product of xj minus xi. So we assume think of the xi as a constant, so and assume xi's are distinct. Then fj of x is 1 and 0 if x is equal to xj, and if x is not equal to xj, no, if x is equal to xi and xi is not equal to xj, right? So fj and fj is a polynomial of degree n minus 1. Now let f of x be f of x, f1x, f2x. I'm adding all these things. Then f of x is 1 for all, okay, for all I. So for f of x I is 1 for all I, right? And this is a polynomial. So f and f is a polynomial of degree and most n minus 1, right? It's the sum of the polynomials of degree n minus 1. Now what does that mean? That means, I mean, it's intersecting y is equal to one line n times. How is this possible? It has degree n minus and most n minus 1. So there's a unique polynomial of that. So f of x is equal to 1 identically. So this means the sum of the product of 1 minus xi divided by, oh no, not 1 minus xi divided by xj minus xi is 1. Right, so that gives me this implication: product sum and product, and xj minus xi, well, yes, so I'm gonna divide it by I, so minus 1 over x, okay, yeah, 1 over 1 minus, okay, minus 1, so 1 minus xi over xj over xi, that is 1. Okay, so that's a key property that I'm going to use. So why is this useful? Because when you look at f of xa times sum product 1 minus xj minus xi minus 1 is what? Sum over all j, now product, and then what you end up is, now this is minus 1 term, so x and a1 up to ai j minus 1 and aj minus 1 and aj plus 1 up to an. That's what we have, right? Because I'm reducing the order by 1. And this is I not equal to j from 1 up to n. Right, so this is sum of the a1 factorial, a2 factorial, aj minus 1 factorial, aj minus 1 factorial, aj plus 1 factorial up to an factorial. Oh, no, not over here. This is at the bottom. This is by induction. And their sum. And this is a1 an factorial. So this is by factorial up to an factorial, and then when you have is this. Oh, there's no product needed, and this is exactly that. All right, that proves the Dyson's conjecture. Now we're going to use this theorem, which was a conjecture of Dyson. We're going to use this to prove an interesting theorem on partitioning the numbers in the pairs. So here's the theorem. It's due to Karasev and Petrov in 2012. So P, let's say P prime, and okay, so let's say it's odd prime. So if it's odd prime, then you have and then p minus 1 is even. So let's say m is p minus 1 over 2. And so let d1, d2, dm be integers not divisible by p. All right. Then there exists a permutation. Let's say x1, x2, xm, y1, y2, ym of 1, 2, 3 up to p minus 1. So we want to permute these non-zero numbers modulo p such that yi minus xi is equal to di modulo p. right? So basically we want to find the pairing of these non-zero numbers so that the difference is exactly what we prescribe. All right, so that's the theorem. And here's the interesting proof by using combinatorial Newstrand. And you can now imagine what we're going to do. So we want to construct a polynomial. And the roots, so if some assignment become non-zero, then we want it to be the solution. So how are we going to do, how are we going to design it? First of all, we want these to, none of this to be, we don't want them to be a 0 modulo p, and product and for all I is less than j, xi minus xj. So we don't want xi to be equal to xj. We don't want xi plus di minus xj. So that means we don't want xj is equal to xi plus dj, and we don't want xi minus x. So we write this, which means that we don't want xi equal to xj minus dj. And we finally we write this. So this means that we don't want xi plus di to be equal to xj plus dj. Right? So this is our polynomial. Now the degree. So this is be a polynomial over the finite field of size p. All right, so the degree, the degree of f is equal to, oh wait, I should have m variables. So m, right? So the degree of this is m plus m choose 2 times 4, right? And this is m plus 2m m minus 1, and we know that m is p minus 1 over 2, so twice m is p minus 1, so m plus p minus 1 m minus 1. Right, and then pm minus well, yeah, so what is it? Twice m is equal to p minus 1, so p minus 1 m plus m minus p plus 1, right? Yeah, so what is it? I'm gonna, maybe there should be a better way of, okay, let me rewrite. So what's going on? So this is 2m squared minus m, right? And 2m squared is p minus 1 times m minus m. So it's p minus 2 times m. All right, that's good. So that means the degree of this polynomial is p minus 2 times m. Right? Now let's us consider the coefficient of product of xi to the p minus 2, right? This is the highest order monomial. So if this coefficient is non-zero, then we are happy because we can apply combinatorial Lagrange. So what is this coefficient? Well, in that case, we can ignore all these DIs, right? Because they will not contribute any of the coefficients in the. So that coefficient will be equal to the coefficient of the product of xi p minus 2 in what? x1, x2 up to xm, and then product of I less than j, xi minus xj to the fourth power, right? So that's the coefficient of the product of xi. Let me subtract m, right? So p, so let's see, p minus 1 is m over 2, no, twice m. So this is twice, p minus 2 was twice m minus 1, and I'm subtracting m, so it's m minus 1 in this product. Something's strange. Oh, no. No, I'm subtracting 1, so p minus 3. We are looking at this. Right? Now, what is the coefficient of that? Now let's go back to this Dyson's conjecture. We take, what is AI? We take AI to be 2 everywhere, right? So then the coefficients and sum of AI minus AI is twice m minus 2, right? So twice m is equal to like p minus 1. So this is p minus 3, right? So then if you look at this, the coefficients of this in this polynomial is equal to that. So this coefficient is equal to 2 plus 2 plus 2 factorial over 2 factorial, 2 factorial, or 2 factorial. So this is 2n factorial over 2 to the n, which is non-zero. Oh, 2m factorial over 2 to the m. And this is non-zero modulo p. This is important actually, in modulo p. Right? Why? Because 2m is less than p. 2m is p minus 1, which is less than p. So we are multiplying numbers from 1 up to p minus 1. And then we divide by 2 to the m. What does that mean? That means 2 has multiplicative inverse, right? So in modulo p, things like this can be equal to like a product of some non-zero numbers, right? So anyway, so that's it. So this is non-zero. That means by the combinatorial Lagrange, there exists xi in what? I can have a p minus 2 choices, right? Yeah, no, p minus 1 choices. This coefficient is, this exponent is p minus 2, so I can have one more choices. So for each of them, I can choose xi from here. such that this polynomial f of x1, x2, xm is non-zero modulo p. This implies that xi's are distinct, xi plus di's are distinct, and then xi is not equal to xj, xi plus di is not equal to xj, xi plus di is not equal to xj plus dj, and xi is not equal to xj plus dj. So this is, so then you take y's I to be equal to xi plus di. Right? Then this is exactly, oh yeah, so everything is a modulo p. Alright, so then you take this modulo p. So that's the proof. Alright, that's it.